All right, I'd like to introduce Preetam Nandy, who's going to talk about A/B testing, and I'll just hand it over to you to dive into your talk. Okay.
Thank you. Hello, BayLearners. I'm Preetam from LinkedIn, and today I'm going to talk about A/B testing. So A/B testing is probably the most reliable method for testing a new method, a new technology, or a new drug. The design of A/B testing is straightforward. You start with a population, then you select a group of people randomly and then assign them treatment A. Then you select another group of people randomly and assign them treatment B. So this works perfectly unless the members are connected by a network through which they can share information. So in this situation, a correct way of doing A/B testing is that you make sure whenever you are assigning treatment A to a particular member, you also assign the same treatment to her neighbors. But in the classical A/B testing design, this does not happen automatically. So in the classical A/B testing design, the neighbors of a member gets random assignment to either treatment A, treatment B, or neither of those. So let me explain the issue with a toy example. So suppose I want to run an A/B test to test the hypothesis whether more money can bring more happiness. Okay, so I have two treatments. One is if you're in treatment A, I'll give you $10. If you're in treatment B, I'll give you $10,000. This is hypothetical, don't get too excited. And so if you run the classical A/B testing design, then what happens is that you got $10, but some of your neighbors has got $10,000. So this is not the same experience as all of you are getting $10, right? So this is an example of the network effect. So if you want to resolve the network effect, you have to make sure that all the neighbors are getting the same treatment, but this is kind of impossible if you start with the A/B testing design, right? Why? Because you may have two members, A and B, such that they have a common neighbor. Then it's kind of undecided what treatment you should assign to them. And also, one member in A could be a neighbor of member in B, then also there's a conflict, right? So to resolve this conflict, what we need to do is do some sort of graph clustering. So at LinkedIn, we run this ego cluster experiment where we cluster the whole network into a set of egos and their alter egos in a way such that no two egos have a connection in between them, and no two egos can have the same alter, right? So if we can make this design happen, then A/B testing is very simple. So we just, instead of randomizing on the randomly selected members, we randomize on the egos. So we just do the A/B testing design on the egos. So we select a random group of egos and assign them treatment A. Then we select another group and assign them treatment B. Then the advantage is because no two egos can have the same alter, so we can make sure that all the neighbors of the egos are getting the same treatment. Moving too fast. So if we do this, then it's a clean design, and if you take measurements, and then it's absolutely fine. But there are a few issues with that. So so first of all, this is a very general solution and works for all types of network effect, as long as you can do the graph clustering, right? But you can imagine as the network gets more and more dense, it gets harder and harder to come up with these graph clusters. So in summary, it does not work well for dense networks. So now we are looking for alternative solutions that works for dense networks. And it has to be that in a way such that it does not require graph clustering, right? Because graph clustering is impossible for dense networks. So here, I'm going to now describe an alternative method, but for a particular type of experiments that we called the exposure redistribution experiments. So what is that? Let me explain to you what is a LinkedIn feed model. So at LinkedIn feed is that so whenever a viewer comes to LinkedIn, they view contents created by other members at LinkedIn, right? And then the feed model is deciding which content goes to which viewer. So the feed model is not only deciding the fate of the viewers, what they're going to see, they're also deciding the fate of the creators, that how many viewers they're going to have. So they have the direct effect on the viewers and some indirect effect on the creators, right? And then, so if a creator has more viewers, they are going to get more likes, share, and comments, so they might be more encouraged to create more contents, right? Yeah, so we can think of feed model as a exposure distribution model, so which is, in some sense, is distributing the exposure of a creator among the viewers. So you can think of the feed model as a giant square matrix, which is denoted by P here. So the Pij, the ijth element of the P matrix, denotes what proportion of content the jth member views that is coming from the creator I. Okay? So the column corresponds to a viewer, which is a probability vector that sums up to 1, and it's defining the proportions. But the rows corresponds to the actors or the creators, and the total sum of the row you can think of as the total exposure that a particular creator is getting. So yeah, we call it this as exposure redistribution experiment because whenever we are comparing two models with different exposure distribution, you can think of the second model is redistributing the exposure of the first model. Okay, so here is an example. So on the top left corner, we have one exposure distribution A, and then on the right-hand side, we have exposure distribution B. And now we want to A/B test which model is better. So we have an A/B test design at the bottom, and we selected the first and the fifth column to give them treatment A, and then we selected the third and the last column to give them treatment B. Okay? So this is all fine. So the columns are matching with what they're supposed to be, but unfortunately, the rows are not matching. So what is the problem? So that the problem is that then we don't have the total exposure for the creators. So in this example, the first column or the first member belongs to treatment A, so their column sum is supposed to be 1.10, but what happens is that their column sum is 0.90, right? And the same happens for the last member who belongs to treatment B. I'm sorry, it's not the column sum, but I'm talking about row sum. So their row sum is supposed to be 0.85, but it's 0.95 in the A/B testing design. So what do? Well, we can cure this issue by assigning treatments to members that are not assigned yet. So here in this example, those are the gray columns, which is the second and the fourth column. And we can assign a new treatment to them in a way such that the row sum matches, right? So we can correct those mismatch by assigning some values. So in this case, we assign 0.20 to the first entry of the fourth column and 0.30 to the last entry of the fourth column so that we have the total exposure matching. Okay, so this cures the problem under some assumption. So the assumption is that the treatment now is affecting the columns of the matrix and also the row values of the matrix. So the row values of the matrix is basically the network effect, and we are assuming that the row values are not important except their sum. So the row sum contains all the information of the network effect to affect the response. So if you make this assumption, then this is how we can resolve the issue. But in practice, we have to resolve this issue just not only for a couple of members, but all members together simultaneously. So how do we do it? We first start with a random design, which is just classical A/B testing design. It's not graph clustering. And then we select some additional nodes randomly to assign them to the new treatment, the treatment C. And how do we choose treatment C? Is by solving an optimization problem. So if you look at the first squared term in the optimization, on the left-hand side of the minus sign, we have the expected total exposure, and on the right-hand side, we have the total exposure after assigning some value to C. And we want to minimize this over all members who have been assigned to treatment. Okay? And then we have some additional constraints. So the constraints are controlling the risk of the experiment. Though the C treatment is, if we let them free to be anything, that might be harmful to members, and we don't want to do that, and we want to control that risk. Yeah. So but we may not be able to solve the optimization completely, so we may not be able to drive the value of the objective function to 0, and we might have several other biases. For that, we do some post-experiment correction as well. So when we collect data on the response, and we also collect data on the observed total exposure and the expected total exposure. And then when we are estimating the average treatment effect, we, instead of estimating, taking the difference between the average effect, we take weighted average, where the weights are given by the expected density of the the density of the expected total exposure and the density of the observed total exposure evaluated at the observed point. So if we do this importance sampling correction, then everything is correct again. Okay, so in summary, we have a 5-step method. We start with a random design, we choose some additional nodes, then we solve an optimization problem to decide what treatment C we should give it to them, and then we run experiment and collect data, and then we finally do an importance sampling correction. So we implemented this for LinkedIn feed models, and one important thing is that we have to choose what treatment C should be, right? If we let it to be any model, then it's too much for the optimization. So here we decided that we are choosing C as the score of the model A times some multiplicative boost factor, right? So then we solve the optimization to get these boost factors, and then we can control the risk of the experiment by having a lower and upper bound for the boost factor in the optimization. And we also update the boost factors regularly to take care of dynamic network and dynamic treatment. Then we finally correct bias with importance sampling. Yeah, we did a bunch of validation. We have theoretical results for robustness. We validate in simulation. And we check that we have uniform p-values in AA test. And we are comparing also with ego cluster whenever an ego cluster experiment is possible. And yeah, so in summary, we have an alternative method for doing network A/B testing, but that works under some certain assumptions, and it's also designed for a special type of experiments, but that main advantage is that you don't have to do any kind of graph clustering, so it works well for dense network. Yeah, this is it. Thank you for your attention.
All right, we have time for a question or two. All right.
How do you compute degrees of freedom if you want to do some statistical testing?
Degrees of freedom?
Yeah.
So the statistical testing would be based on the final importance sampling corrected values. So it would be just, you can assume to be normal distribution, just regular t-test.
Yeah, but the issue here is that there are dependencies between the different observations, right? And degrees of freedom is supposed to be number of independent observations, and I thought the whole point of your model is that you're trying to handle that issue.
Yeah, so there is a dependency in terms of the treatment, but the response is independent. So that's why you can do still the t-test, yeah.
All right, can we thank the speaker one more time?